We ready? Okay. Great. Welcome back to the last lecture of my series and also to the last lecture of this school. I'm sure that you've been through a lot. Okay. So let me summarize what I did yesterday, so where we are at the moment. So I was talking about quantization of a theory with a given Lagrangian. I said that, well, if we have the action that can be split into free and interacting piece, we can quantize the free theory first. So this quantization, this leads to several structures. So there is the star product, there is the time-ordered product, the renormalized one, and there is also the classical VV operator, which is the bracket with S0, as well as the quantum VV operator, okay, which is given by the twist with the time ordering map S0 T. And then I also introduced the interacting BV operator, so SV hat, and this was given in terms of RV. So let me write it down here as well for reference. Okay. Time ordered. Sorry. Maybe I need a bit more room because this is a bit too crowded. Sorry about that. RV of F. Okay. So IH bar time ordered V minus 1 star IH bar, time ordered V, time ordered with F. Okay, so this guy is defined again as the twist of S0, but with this map. So this is called the retarded Müller operator. Oops. Okay, so that's the structure up to now, and I've been focusing on the situation where this is a Lagrangian of the scalar field, so that we don't have to talk about gauge invariance. So that mainly affected what the BV operator was. And I formulated here also a very important quantum master equation. Okay, so there are two ways of stating it. So one can be stated in terms of essentially the invariance of the S matrix, okay, under this BV operator, or equivalently, you can write it down as 1/2 S with S minus IH bar delta of S equals 0. This is now the renormalized BV Laplacian. And that goes together with also the free version. So 1/2 S0 with itself minus IH bar delta S0 equals 0. Okay. So this is where we are. So now actually it turns out that going to gauge theories is not that hard as you might think. It's just going to modify a bit the space of fields. So we are going to extend the space of fields a bit. So let's go back to where I introduced this BV operator as 0. I showed you the Koszul complex. So let's go back to that point. So we had the Koszul complex here, V and so on. So this is degree 0, minus 1, minus 2. Okay, so I looked at the 0 of cohomology, so what happens here, and I said that the 0 of cohomology of this complex gives me the space of on-shell functionals. So, and here the differential is as 0, and well, in this simple case, as 0, it's just the Koszul operator delta. Okay, so now let's look at what happens in this slot. So we know that H0 of this complex gives us on-shell functionals. Now let's look at the cohomology at degree minus 1. So what happens? Let's first look at the kernel. So the kernel of S0, okay, at degree minus 1. So this would be vector fields such that if I insert the equations of motion one form, so d S0 x has to be a kernel, so this is identically 0. So this is identically 0. How could we interpret those vector fields? So this, recall, this is the Euler-Lagrange derivative, so variation of the action. So vector fields that satisfy this correspond to the direction such that the variation of the action vanishes, right? So these are directions where the action is constant. So, you know, if you think about your course in classical mechanics, well, these guys will be the symmetries. So these are symmetries. Namely, they describe directions in the configuration space such that the action is constant along these directions. Okay. So that's probably a good way of, you know, talking about symmetries. Now, before we get to, you know, some particular examples, just looking at this complex, obviously we're having a kernel here, but what's the image, right? So in computing cohomology, you have to take the quotient of the kernel through the image. So what's the image? And, you know, by definition, the way we set things up, S0 squares to 0. So obviously, you know, the image would be contained in the kernel. So what are these things in the image? So let's try to describe those. So image of S0, again, here in degree minus 1. So let's look at an example. That maybe is a good way of doing this. So let's take an element in that space of bivector fields, right? Antisymmetric tensor product of two vector fields. So x, y are both vector fields. And let's see what happens, right? So we are going to apply a 0 to that. Okay, so I said before, as 0 on multivector fields is done using the graded Leibniz rule. So this is S0x times y. This is now a function. This is still a vector field. There is a sign, right? Because we have to commute this past here. So this is y times, sorry, x times S0y. Okay, and then, well, obviously, right, you can see that now if I apply S0 again, right, then I will have the difference of two terms that look the same. So obviously, well, luckily enough, we have not made a terrible sign mistake, and this is indeed an element of the kernel. So mathematics is safe. But what is it exactly? So if we now plug in the definition here, so this is ds0x times y minus x ds0y. So what is special about it, okay? What's kind of maybe slightly awkward about it is that you see it has this equations of motion, one form here and here. So when I evaluate this guy at the solution, solutions, remember, are a zero locus of this one form. This vanishes, okay? So this, this vanishes on the space of solutions. Okay, so this is by definition phi such that ds0 of phi equals 0. And this motivates the name for such symmetries, for such vector fields, trivial. So these are trivial symmetries because if we are working on shell, if we are working on the space of solution, then we don't see them, right? These vanish on the space of solutions. So these are called trivial. So this is trivial symmetries. Okay, so now there is a nice interpretation of the cohomology in degree -1. So h -1 of S0, what is it? So this is the kernel, right, which is symmetries modulo trivial symmetries. Trivial symmetries. Okay, so, well, obviously, okay, this symmetries modulo trivial symmetries is non-trivial symmetries. So these are things that would appear in gauge theories, but wouldn't appear for a scalar field. Because trivial symmetries, as you have seen, well, I can have them always. They're always there. These just arise from the way I set up my Koszul complex. But what we are really interested in is non-trivial symmetries. So these are non-trivial symmetries. Sorry? No, it's not. It has to be proven. Yes, it is true. So, okay, this is a very, very good point. Okay, so this is the same as we did in degree 0 when we had to show that things that vanish on the space of solutions are, well, in the image of S0, right? So one has to show that all trivial symmetries are in the image of as 0, okay? And here I can give you, again, a reference. So sort of general introduction to these things is the book of No Teitelbaum. So book. But it's a known result. There are refinements of that, but one essentially uses a change of variables on the jet space and the fact that everything is local or multi-local. But yeah, that's a non-trivial point. Okay, so now I know that H minus 1 is telling me something about those symmetries, so I can use it to detect those symmetries. Now, in physics, we want to be a bit more specific about that and characterize this space in some way. So I'm now essentially going to pass to a particular situation where these symmetries are given by the action of some Lie algebra. Okay, it could go more general. You could do a Lie algebroid, but I'm going to restrict to the situation where we have a Lie algebra action. And that covers, for example, Young-Mills theories, that covers gravity. So there are some nice examples to think about. But yeah, in general, you want to work with at least a Lie algebroid. Okay, so now let's assume that non-trivial symmetries are given by some Lie algebra action. Oops. On the space of configurations. So let's take a Lie algebra G, okay, and let it act on the space of configurations as follows. So there is a map sigma going from G cross E to E, okay? So here we have some gauge parameter, some element here, and then we can, for the pair of such things, I get sigma of psi acting on phi, and this action also induces an action on the functionals. So on functionals, okay, so we have rho of psi of, let's see, no, maybe slightly differently. So this is a Lie algebra, so it comes from a Lie group action, right? You can essentially use the pullback to define the action of that Lie group on a functional. So there is a map then from this Lie algebra to the Lie algebra of vector fields. Okay, vector fields are derivations on functionals. So there is a map psi, again, coming from this Lie algebra, maps to partial psi, which is a vector field in here. Okay, and now if I want to write this down explicitly, then I have a map from the space of functionals. So F, take a functional here, and then act on this with that vector field. Okay, and this is again, well, sort of canonical. So I take the derivative of F, so I take the one form which is given by the Dirac differential, and then contract it with that vector field d psi. Okay, so second, so this is insertion of, again, one form into a vector field. So again, gives us an element of F. So that's very broad at the moment. And I'm going to make one more specification. I still want to work with things that are actually sections of a vector bundle. So another assumption, assume that G is again a space of section of some vector bundle G over M. Okay, so I think that's it for the notation. And now, well, you can probably guess from the structure that this very easily generalizes to a Lie algebroid. A particular example I want to think about is Young-Mills theory. So, example, Young-Mills. Okay, so here the action, again, well, this goes back, I think, 2 lectures. I wrote it in terms of a generalized Lagrangian with a cutoff. So I wrote the action in this form, L Young-Mills. It's a function of a vector potential A. So A is, running out of good notation, is a one form on M valued in some Lie algebra K. And this was minus, maybe 1 over 2 F wedge star F. Okay, still with a cutoff where F is dA. Okay, so that's the example, and the symmetries. Well, we know what the symmetries of Young-Mills are. So I can change A by adding something exact. So symmetry. So A maps to dA psi, where psi is the gauge parameter that lives in smooth functions on M valued in my Lie algebra K. A very simple example here would be to take electromagnetism where this guy is a billion, so this is valued in R. Questions?
Yeah, sorry, so why you make a distinction between when you introduce a new thing, what you change the data?
Because I was just working with an example. I mean, yeah, so this in the old thingy, this is G. This is the fracture G.
I assume for defining this theory, you assume some simplicity or something, and maybe compactness of
No, well, I mean, not necessarily, right? Because I guess, okay, no, compactness, yes, that's right. Compactness of, you mean the Lie group, or, yes, that's right. Yeah, sorry, but not the manifold, obviously, yeah. So that's the sort of standard example, and now I want to well, I want to do two things. One thing is that I want to package those symmetries in such a way that I amend my Koszul complex and somehow, I fit them into that structure. And another thing I want to do, I'm talking here about on-shell stuff, on-shell functionals, but if I have a symmetry, if I have a gauge symmetry, I'm actually interested in studying invariance. So there are two things, right? So one, study invariance, and the other is maybe amend my equations of motion part of the complex to account for the fact that I have symmetries. And this actually can be done in a sort of one go. So I would start with finding a cohomological interpretation of this story. So what does it mean to have invariance? So here there is this formula on how symmetries act on functionals. And now I'm interested in functionals that are invariant under those symmetries. So that are invariant under this Lie group, Lie algebra action. And there is a nice gadget in homological algebra that does just that. So given Lie algebra action, you can describe the space of invariance as cohomology of a given complex. So this is called Chevalier-Eilenberg complex. So Chevalier-Eilenberg complex. Okay. So I take my Lie algebra of symmetries, and I take antisymmetric forms, antisymmetric functionals on that, valued in the space I'm acting on, so valued in F. So the underlying algebra here is G star, should maybe G prime, because I mean like actual honest dual, continuous dual, tensored with F. Okay, so there's going to be some cheating because I don't want to necessarily cover, this is arbitrary degree. I don't necessarily want to cover all of locally convex differential calculus in like 15 minutes. That would definitely be shortchanging you. I'm just going to say that there is some completion of this tensor product that I need. So the algebraic tensor product is not enough. I need some completion. In practice, I'm just always going to work with things that are smooth functions, smooth sections of some bundles. But to make this happen, one has to make some completion. So this is appropriate completion. Okay, so that's my algebra, and now my differential. So first of all, I want this differential to kind of describe this action. So in degree 0, when I act on a functional, so f in f, okay, so then this differential gamma of f, so this should be what? This should be one form, right? So this should be, well, just an element of, G prime tensor F. So it eats one element of G and spits out a functional. Okay, so how do I want to do this? Well, this guy here, right? This is a functional. Actually, maybe I can also use another piece of suggestive notation. I can write this as follows. Okay. So here, this eats up psi, which is my gauge parameter, and then spits out the psi f, which is a functional. So great. So that does what we want. Now, also I need to specify what happens if I act with gamma on one form on G. And here there is an obvious candidate for doing that. So how do I make a function of two variables in the Lie algebra from a function in one variable? Well, I can pull back by the bracket, the Lie bracket, which kind of comes natural in our story. So if I now have, so omega is now a 1 form, so it's in G prime, just that. So now I want this to be a function of two arguments. Okay, so what I'm going to do is say, and signs, sorry, I have to check that. So this is just the commutator of xi1 and xi2. Okay, so with these two prescriptions, I can now extend gamma to this whole space, and also I require the thing to satisfy graded Leibniz rule. So plus graded Leibniz rule. So this is extend to the whole space. When did we start? Sorry, I'm getting confused with these things. Okay, so I have plenty of time. Now there is a piece of notation that's usually used in this context. So I think Pavel mentioned some ghosts, yes? Oh, that's correct, sorry, yes, thank you. Oh, good, people are paying attention, great. Okay, yes, that's right. I ran out of space and that's why I felt compelled to compress. Okay, so that's omega, of course, of the bracket. Thank you so much. Okay, thank you. Yeah, so you have a one form, and this object here is now a two form. Good, ghosts. Yeah, I promised ghosts. So these forms here can be nicely described by a little trick. So we're thinking about antisymmetric tensor products, right? There's an exterior algebra of that. We're thinking about functionals on this space of gauge parameters. So actually these functionals on this space of gauge parameters are typically denoted in terms, described in terms of anti-commuting variables. Okay, so here, note by the way, one uses evaluation functionals. So now I'm going to write something sort of coordinate dependent. So we're going to have, let's see, up or down. Never do indices, so yeah, it doesn't really matter, but let's say down. No, okay. Whichever. So it's the A component at a point X. So this is evaluation. I'm evaluating a section of some vector bundle in a particular coordinate system. I take component A and I evaluate it at point X of the manifold. So this acts here on Xi, which I said itself is a section of some vector bundle, okay? So this is obviously a particular component there. So I have those evaluation functionals, Okay, so I can write these formulae up there in terms of evaluation functionals. And because I'm in the exterior algebra, right, so everything anti-commutes, so I take their anti-symmetrized tensor products. Okay, and these things are called ghosts. So these are ghosts. Okay. How do I want to describe that? Let's look at an example of the Yang-Mills theory again. So using this notation, I can now write gamma A. So now here, we are here. Okay, so I can write it in terms of basic fields. So gamma A will give the covariant derivative of the gauge parameter. So I have to insert here the placeholder for the gauge parameter, which is this evaluation functional. So DAC. And then this thing with the commutator, I have gamma on C. And because there is an extra anti-symmetrization involved, there is going to be a factor of 1/2. And then there may or may not be minus sign depending on what convention we are taking. So maybe let's do without a minus sign. But yeah, these things vary a bit. And this might be more familiar from, say, physics textbooks. You hear about the BRST formalism, or, well, BV formalism as Pavel presented it. You will see formulas like that. And these guys are called ghost fields. But if you want to think of them more abstractly, one way of doing it is to think of them just as this antisymmetric forms on the space of gauge parameters. So that's the setup, and now let's see if we can apply the same methods I introduced for the scalar field to also treat this situation. Let's go back quickly to this underlying algebra of the BV complex, of the Chevalier-Eilenberg complex. What does it have here? So this piece is understood, right? We have already talked about functionals. Now, this piece is something like functionals, right? I mean, this is antisymmetric forms. And if you studied some graded geometry, you will immediately recognize, well, you know, this is the space of functions on a graded manifold, right? So you can assign a degree 1 to elements of this space of gauge parameters, and then natural sort of space of functions on that would actually be just the space of antisymmetric forms. So let's do it here. So in graded geometry, okay, so this fellow can be seen as the space of functions, and again, I'm going to specify multilocal. Okay, this is multilocal functions on the graded manifold. So this was functions on E, and now I want this in degree 1. Again, you don't have to erase everything, but I'm just going to make a shift. Sorry about that. So G prime tensor F, this is O multilocal, E plus G, let's see, goes degree 1. Okay. Now, this is, of course, a bit formal at the moment. I would have to tell you what do I mean by this space of functions and what do I mean by multilocal. Again, this is maybe not that hard, but complicated. So I'm just going to send you to a reference. Well, a good reference for all of this would be my book. So in particular, it has that information there. So PAQFT, Introduction for Mathematicians. Okay? And in one of the beginning chapters, there is a precise definition of what I mean by functions on such graded manifold, and in particular, what I mean by multilocal. So some analysis is needed. Okay, but now the key point, however, is that, again, we can phrase everything in terms of a space of functionals of a particular type, in terms of regularity and other properties. So let's call this guy E bar, and let's think of it as extended configuration space. So this is extended configuration space. Okay, so now I want to repeat this this Koszul construction. So what I did last time, right, was to take multi-vector fields on E. That's how we got the Koszul complex. So now let's take multi-vector fields on this extended configuration space. And I'm going to use another piece of notation from graded geometry, which is actually pretty useful here. Okay, so multi-vector fields can be understood, again, as functions on something like a cotangent bundle, but I'm going to shift it by 1. So you remember anti-fields were anti-commuting, so that's a degree shift. Now this generalizes also to graded manifolds, so I'm going to take a degree shift. So this is degree shift, degree shift on the fiber of extended configuration space. Okay, and just again to compare with what we had before. So if I just had the configuration space without that extra bit, that was, so it's again functions on that. Shifted. So that is the same thing we had before, so multi-vector fields. Good, so at the moment I'm just playing with these formulas, so I'm trying to repeat this construction, and well, that would already give me, again, the underlying algebra of the differential complex I want to build. And now I want to combine the two differentials. So I had the Koszul differential, which comes here from the action, and I have the new piece, which is the Chevalier-Allenbeck differential. So now I want to combine the two. Any questions up to this point? Because I have thrown a lot of stuff at you. Is it okay? Cool. So let me just give you one more piece of machinery, and then we're going to take a break after I get the BV complex. So when I was talking about the Koszul differential, I said that, oh, it can be nicely written in terms of the bracket. So recall that locally S0 could be written as the bracket. Actually, well, we don't really need to specify to S0. So the Koszul differential delta S was written as the bracket with the action. So now the question arises, can I write the Chevalier-Allenbeck differential as the bracket? Well, here we still have the space of multi-vector fields. We still have the bracket. Can I write gamma also as the bracket with an action? But now an action is going to be a local functionals on this slightly extended space. Okay, so the answer is almost there, actually. So these, the expression for gamma, so gamma as such, modulo the fact that you have to smear things with a test function, but this is maybe secondary. Gamma itself is an element of this space. And this is because, well, I mean, it's clearly a derivation, right? So it's actually a vector field in this space of, well, multi-vector fields. So in particular, I can write now this differential as the bracket, let's say, I usually call it theta in my lecture notes, so let's call it theta, which is essentially built from these pieces. So theta of f, and let me write it down for the example of the Young-Mills. So this is DAC. So this is how gamma acts on A, right? So write it as a vector field. So D over dA gives DAC, and plus, and this is how gamma acts on C. So the corresponding vector field is 1/2 C with itself D over DC, right? So it's a vector field. Hence, oops, I should also have an F here, not forgetting that. Okay, it's a vector field, hence, in particular, an element of the space of multi-vector fields. Both guys can be written locally as the bracket with something. So now I can use this object here to actually modify my action. Okay, so I noticed that the Chevalier-Allenbeck differential is a bracket with some Lagrangian. So a natural thing would be to now extend my initial Lagrangian by this extra piece. So let's do it here, and then I will have a break. Okay, so now extended Lagrangian or extended action would be the original guy, so let's say Young-Mills, plus theta, which implements the gauge symmetry. And the extended differential, so S, which is now, spoiler, our BV differential, is again the bracket with that extended action. So this is classical BV differential. Okay. I think it's good time to have a break. Any questions before the break? Yes. Okay, good. Spoiler alert. Yes. So obviously I want, so let me maybe say it now. So I want this, of course, to square to 0. So this is guaranteed by this relation, which is the classical master equation. Classical, master equation. So this is essentially the condition for S extended. Now, what happens if it doesn't, right? So that would be a bit of a disaster. So if after this extension I don't get an action which satisfies this, then I have to correct things. So then there is, this whole methodology of using homological perturbation theory, add more terms, try to look for a solution. And in nice cases, this terminates after finitely many steps. In not nice cases, it doesn't. But I'm just talking about nice cases. So if not satisfied, use homological perturbation theory and add more terms. Luckily enough, in Young-Mills, which is my leading example, this is satisfied on the nose. I don't have to do anything. But yes, thank you for the question. Anything else? Okay, so again, I'm going to linger here in case people have more questions. Thank you. Should I start or? Okay. Right, so before the break, I defined now the full BV operator for the situation with symmetries. I stated this condition for this to be honest to goodness differential. And well, in the case we are looking at here, so this is the simplest case where we have the Lie algebra action, and well, we can actually show that, say, in Young-Mills or gravity, simple examples, this condition, the classical master equation, holds on the nose. We don't have to extend anything. And we just have the BV differential as the sum of Koszul and Chevalier-Eilenberg. Okay, so here, simplest case. But this already covers quite a lot. So this is this delta S plus gamma. But actually, okay, so maybe there is a question here. Should I use delta S as we have it here, right? Yeah, so yeah, should write like this. Yeah, so delta S itself gets also modified by the fact that we are now taking the bracket of this extended action. So it's still true that we have Chevalier-Eilenberg differential, and we have something which can be identified as Koszul differential, but there is an extra bit coming in from the ghost part. So this is no longer just the Koszul. This is what one calls Koszul-Tate. So Tate differential. So just to make things a bit more systematic, what do we have here in this whole structure? So we have several gradings. We have a lot of variables. This is generally speaking a bit of a mess. So let's revise what we have. So first of all, there is this grading of the underlying extended configuration space, right? So we have these ghost variables which come with degree 1. Our basic fields we've started with come with degree 0. And then we also take this degree shift on the fiber where we take the cotangent bundle. So the elements on the fiber will have a further degree shift. So let's maybe summarize this. So summary. Okay, so we have fields, and let me just use the Young-Mills example for illustration. So we have fields. Okay, so these are degree 0. So traditionally, this degree is called ghost degree. So this is ghost degree. Okay. What else do we have? We have ghosts. So we have these guys. They have degree 1. So maybe I don't have to write degree again. Now, there is an extra grading coming from the fact that we have this shift on the fiber. So we talked about anti-fields, right? So anti-fields are these generators on the fiber. So in particular, we have the anti-field for A. So they also come with their own label because we want to keep track of who's anti-field and who's not. So there is anti-field number. So these are not anti-fields, so they will have anti-field number 0. This has anti-field number 1. Sorry, yes?
Yeah, your anti-field number sort of differential of a space of fields degree?
That's right. Yes, yes. So the sort of differentials on the space of basic fields, well, so the degree shift is always by 1. So on the space of basic fields, we shift by 1. So this is 1. On the space of ghosts, so they also have their anti-fields, shift by 1. So this is 2. So here I can write down, so this comes from, well, 0 plus 1, and this is 1 plus 1. Okay. And there is also something which is called a total ghost number, or maybe just call it total degree, okay, which is given as the ghost degree minus the anti-field. So this is here 0 minus 0 is 0, 1 minus 0 is 1, 0 minus 1 is minus 1, and 0 minus 2 is minus 2. So here is the total degree. And we can also expand this differential in terms of these various gradings. So in particular, if we look at the anti-field number of these various pieces, delta is going to change the anti-field number by 1. So this is it would have anti-field number 1, and gamma doesn't change the anti-field number. So it has anti-field number 0. Okay, so there is this whole menagerie of things, and then in practice, you're interested in, well, using this machinery for, well, first of all, finding the invariants and then finding the on-shell functionals. So let me just finish with summarizing, well, what physicists want from all of that. Yes?
Sorry, so the delta and gamma are created with respect to the total degree?
Yes, so yes.
So we are not seeing the form degree that, for example, A could be a one form when it's a connection, so it doesn't see this degree?
Oh, you're talking about the degree as a form on the manifold.
Yes.
Yeah, that is, yeah, that's not included here. Yeah, that would be, so these are sort of two directions. So from that you get a bicomplex, which I'm going to draw in right now. If you want to include also form degree, then you get a third direction. So you get.
And this differential doesn't see it anymore?
No, not really, no. You would have to, yeah, if you can extend, you add the DRAM differential, and then you have total complex, which also does that. But I typically don't, well, not for today. Yeah, so this works on functionals, right? If I'm working on functionals, then everything is sort of integrated out. So I don't worry about forms. Now, if I want to extend and work in P forms, so like local, not local functionals, but local forms, then yeah, but that's not for today. Yeah. Okay. Yeah. But yeah. I guess maybe, yeah, so for the version with P forms, there is a paper, the recent paper of Owen William and myself, where we do yet another direction of this. Okay, so let me write down the resulting bicomplex. Okay, so we have first, the Koszul part. Okay, so this horizontal part is going to be delta. Here, this action of delta is exactly the same as we had before. So, okay, delta, and so on. And there is the vertical part, which corresponds to this Chevalier-Eilenberg complex. So this is gamma. So this is gamma. It goes to F, so on. And then, obviously, you get the mixed pieces as well. So here you have this naturally extended gamma. So you have this tensor V, okay, and so on. So you can probably just carry on. So this is, bounded on the right and on top, and extends to infinity to the left and to the bottom. Let's see. So the anti-field degree labels the columns. So this is the anti-field, and this ghost degree labels the rows. Ghosts, and then the total degree here is, the total degree of the total differential, right? So this is this minus that is the grading for the total complex. Okay. Now, an interesting fact that I'm not going to prove, but just state, is that with this setting, if we included the symmetries in the construction, this horizontal complex becomes a resolution. So here, this is a resolution. What does it mean? It means that all the cohomology is concentrated in degree 0, which we have computed. This was the on-shell functionals. But by adding this extra piece to our Lagrangian, by extending the theory with the Chevalier-Eilenberg piece, automatically here you also get I should have written it here. So here you get an extra piece which contains the non-trivial symmetries. So this is non-trivial symmetries. Okay. Yes. Mm-hmm.
Here you are assuming that you add all the necessary ghosts, all the necessary.
Sorry, what?
Here you are assuming that you have already added all the necessary ghosts for ghosts.
Yeah. So I assume that this is it. There is nothing else. If there's no ghosts of ghosts, there is nothing else. There's just that.
No, but when you take
Uh-huh.
the resolution,
Mm-hmm.
add, you have more like terms of these ghosts or.
Yeah. Yes. Sorry, I'm not understanding the question, probably. I have more terms.
This very
Huh?
painful kind of modify now because you are assuming that it will
In principle, it's not.
So you have to add something?
No. Okay, no, thank you. This is a good question. This comes out from the package somehow. So let's see. Let's look at the anti-field number. So I said that the columns are labeled by the anti-field number, right? Okay, so anti-field number 1 is just vector fields. Anti-field number 2, we have the old stuff, but we also have a piece which is coming from these guys, from the anti-fields of ghosts. So anti-fields of ghosts, they have anti-field number 2. So they live in this slot. So they are extra generators, extra variables that get added here if we expand things in these 2 gradings. And then, the action of this differential delta, okay, so delta is defined as the anti-field number 1. Maybe anti-field number -1 because it lowers the anti-field number. This is anti-field number -1, okay? And the way it acts on the anti-fields of ghosts, it kills the non-trivial symmetries, okay? So this exactly describes, this extra piece that appears here exactly describes the non-trivial symmetries. I think, I would probably need a lot more time to explain it in detail, so I'm not going to attempt it because then we would never leave here. But comes by construction. Okay, but this gets really technical. So I don't know. There's always a point in this BV story where things become very complicated very quickly. Yes.
But my point is that
Yeah.
the complex now doesn't necessarily represent anymore the sheaf of functions of the shifted protein from there to upstairs. Because now you have extra variables.
Want to bet? Okay. No, you're probably thinking about a more complicated situation, because it is true that the BV complex by complex is not always the space of functions on some shifted cotangent bundle. That is correct. But in this case, in the simplest case, it is. So I'm just talking about the simplest case where you take the shifted cotangent bundle, you take functions on that, and then extended differential. That's all there is. So, but of course, yes, there are cases where this is not true. Okay, I think that's it for sort of dip into gauge theories. I think, so you can now take that and combine it with the lectures of Pavel and extend it yourself to the theories with boundary. No? So now this is essentially the classical story, okay? Now, the great advantage of the way I set things up yesterday is that, there's actually almost no modification to what I said in this sort of complicated situation with these all crazy variables, degrees, and so on. So to do what I presented to you before, you just need some action. We have action. The bracket. We have the bracket. And that's it. The only difference is that right now I'm working on a graded manifold, okay? So the whole story from yesterday extends to this example where I replace my configuration space with this extended configuration space and the action with the extended action. So that is the summary of this story. So now, quantization. So if you don't want to be bothered with this business, you can ask your friend to give you a graded manifold and an action, and that's it, okay? And a nice bracket to go with it. So replace E with the extended guy, replace S with S extended, and again, here I'm working on the shifted cotangent bundle again, so we still have the same bracket. So still have the Schouten bracket, and then you run essentially the same game. What you might notice if you start doing it is that, well, as Pavel said in his lecture, you might want to do the gauge fixing as well. Okay, you can do the gauge fixing. So maybe your extended configuration space has to have even more auxiliary fields. So potentially further extend with well, there are fields called anti-ghosts and Nakanishi-Laubtrup fields. I think that was also mentioned. Anti-ghosts, and here Nakanishi-Laubtrup fields. Okay, maybe do the gauge fixing. Okay, but these are all sort of manipulations you do on the level of classical theory, right? You can mess with those fields, you can add more variables, you can change the differential. You know, all of this happens in the classical theory. But then the quantization has the same structure. You have functions now on the graded manifold. You construct these star products, star-ordered products, and it runs exactly the same. So that, I think, is maybe a consolation that if you haven't understood everything or anything or only a part of this story, if you're just interested in quantization, maybe that's not a tragedy, okay? You can just take the textbook Lagrangian, plug it in, and still be happy with the quantization. Okay, any more questions up to this point? I'm now going to shift gears and go back to more general renormalization story before we finish. So any more questions to sort of gauge theories business? Okay, how much time do I have? 20 minutes, okay. Infinite, because it's the end of the conference, right? That's how it works. Okay, so I want to finish with some remarks on renormalization. So, back to renormalization. So I said that this quantum master equation is a serious business, and we really need it to be able to quantize things. So quantum master equation in the renormalized form, that was, well, we should better start with the free theory which satisfies it. Okay, and then our interacting theory should better satisfy it as well. Whereas here, these are the renormalized quantities. And why did I need that? I needed that to conclude that S hat V for, well, just on the margin, S is S0 plus V, that the interacting BV operator is local. Okay, so that was the computation I did before. So SV was defined as RV minus 1 composed with S0 composed with RV. And to conclude that this was local and written in a nice way, I needed this quantum master equation for both free and interacting story. So then that gave me the nice result. Okay, so how do I do this? How do I make sure that the quantum master equation is satisfied, and what if it isn't? So in practice, one can show that if you're given, some prescription for the time-ordered products, you have a lot of time on your hands, then you compute, right, and you find out what this piece here is coming from the renormalized BV operator, BV Laplacian. Then typically we start with the theory which satisfies the classical master equation already, okay? So presumably this piece and this piece would be zero independently if the theory satisfies the classical master equation. So somehow this renormalized BV Laplacian might pose an obstruction to satisfying the quantum master equation if you already have the classical piece equal to zero. So then you think, all right, so how do I do that? Well, maybe I should add something to the classical piece in the order of h bar, right? That's going to kill this term. Oh, the zero, this is zero, this is zero. Fine, order h bar equals 1. Well, order 1 in h bar, you have obstruction from this one, so you might want to add something here. Okay. So let's sketch out the strategy. So how to satisfy this? Okay. So order h bar power 0, we have this as long as the classical theory is good. So if the theory satisfies classical master equation, and then order h1, I want to add something. So add something to S. So let's now say W is S plus H bar W1, okay? So that W with itself, so now we are looking at order H bar equals 1, so minus I H bar. Now, careful, this guy can also have higher orders in H bar. Note that this is the renormalized quantity, so can have higher orders in H bar. So this, now I have to look at H bar equals 0 of that quantity itself. So that deals with H bar equals 1. Right, so this I also have to restrict to H bar equal 1. Now, obviously, you might not be able to add something to S such that this holds. And in order to show in a particular example that this is possible to add something to S so that you can solve the next order, this is some cohomological condition. So there might be some obstructions to do it. So say sufficient condition for this to work. Okay, so this can be nicely phrased in terms of some, well, I mean, going back, it can be phrased in terms of cohomology of, oh, okay, to say it so that it's not complicated. So you're looking again at the classical BV differential. You're looking at the cohomology of this Lie algebra action. So there are some conditions that you can put on the Lie algebra itself and the sort of content of the theory that this works. So again, I don't think this really is enough time to talk about it. So sufficient condition for this to work. So this has something to do with so some cohomology vanishes. Okay, so and if you want to look at the details, there is a lot of work in that direction. There are the papers of Enod, Teitelbaum, and collaborators where some of these things are calculated in detail. Okay, so references, for example, again, etc. But there is also another way of phrasing this. So instead of adding things to the action, I could also think, well, maybe the way I renormalized things in the first place was silly. So maybe there is a way to choose renormalization freedom. I told you there was some freedom at the beginning, such that this term vanishes, so that I'm only left with the classical case. So here is another way of thinking about it. So alternatively, or actually it turns out equivalently, so use renormalization freedom to redefine the time-ordered product itself. This is actually a very nice piece of, well, Epstein-Glaser and randomization theory. How do I account for this randomization freedom? How do I keep track of how things are changing when I redefine time-ordered products? I said that, you know, these extensions, these things exist, but they're not unique. But what does it mean, okay? How this non-uniqueness affects the theory. So this is related to the notion of renormalization groups. I want to finish with telling you just a few words about renormalization group and how it affects what's going on here with this quantum master equation. So very crude renormalization group. So this is, there are many things that people mean by saying renormalization group. So here I mean something that goes back to Stückelberg, Peterman. Okay, so they say, well, so what's a renormalization group? This governs how the action, how the theory changes under adding counterterms. So primarily, this contains maps on local functionals that add counterterms that change the theory. So in the first instance, this is maps from F log, formal power series, to F log. Okay, well, that's clearly too much. So then there are some conditions which these maps have to satisfy to deserve the name renormalization group transformations, but there is not that many. So here, well, the axioms, the properties of this renormalization group. So these maps, well, this is sort of like starting condition. So at 0, you get 0. So renormalization group, let's give it a name R. So here Z is an element of R. There is a condition on the first derivative. This is an identity. And there is a condition that resembles the sort of factorization condition we had for the time-ordered products. So this is a nice one. So if we have 3 functionals, they correspond to different actions, different local interaction terms, such that the support of F1 does not intersect the support of F3. Then this splits. In a very similar way as we had with, factorizing, the time-ordered product. Okay, and this is again something like a causality condition. Okay, and there are some more, but they are not very relevant to this story. So this is actually the most important one. So these characterize the randomization freedom, so the ambiguity in defining the time-ordered product. So this is the last statement I want to make. So there is something called the main theorem of renormalization, which says that if you have t and t tilde, time-ordered products from Epstein-Glaser renormalization, from e.g. renormalization, the following are equivalent. So you can take your new time-ordered product, okay, and then take the S matrix with that. But alternatively, the statement is that I should write it here. So there exists a unique element of that renormalization group such that taking this time-ordered product is the same as taking the old one, but applying this renormalization group map to V. This is a very cute theorem. It tells you that redefining time-ordered products is essentially adding counterterms, because these maps on local functionals, they can be thought of as adding counterterms, so adding terms to the action. So you can either add terms to the actions or just redefine time-ordered products. So now, going back to quantum master equation, this is exactly the prescription how to relate two ways of solving quantum master equation. So you can either be lucky and come up with the prescription for time-ordered products such that there is no anomaly, there is no delta there, that you have quantum master equation just reduces to the classical master equation. Or, well, you're not that lucky, but then you can correct this by applying appropriate element of the renormalization group. So that would correspond to adding counter terms and solving the quantum master equation. And there is another fact which I also showed in my paper, that if you find a solution to the quantum master equation, then this is stable under the action of the renormalization group. So solutions to QME stable under action of R. So R maps solution to solutions. Okay, I think I've been talking for long enough. I thank you very much for your attention, and well, floor is open for questions. Thank you. Yes.
So, to be sure if I understood well what you mean by the power of the product. So, you could like take any QMT textbook,
Yeah.
change the time of the product to a convenient one, and not have to do the renormalization part.
Well, no, I mean the time-ordered product here, I mean the renormalized one. So when I say redefine time-ordered product, I said, well, you know, you used the cutoff, and this is clearly violating your gauge invariance. You got an anomaly term. Well, maybe you should have used dimreg. You use dimreg, and then miraculously you arrive at the situation where you don't have the anomaly in that equation. That's redefining the time-ordered product. Right? And this theorem says that, well, if you want to stick with your original regularization, you can, but then you would have to correct the action somehow. You have to add further terms. But it also works the other way around. So if you don't want to be bothered, you know, you can say, well, So, okay, so I have some potential anomaly, I have some delta, and then, you know, like in Young-Mills without chiral fermions and in sort of nice theories, you can show that you can always redefine your action because some cohomological conditions are satisfied. So either you come up with a prescription that explicitly gives you what you want, or you find some nice theorem that tells you that you can always correct it. But yeah, this tells you that this is essentially equivalent, if that makes sense. Yes?
That's a very naive and broad question. So how do you phrase in this framework the problem that is posed by general relativity, like the quantization of general relativity?
Right, so, okay, so general relativity actually is with the metric formulation. So if you just look at Einstein-Hilbert action with the metric perturbation, this is in the class of not so bad theories. So what they presented for Young-Mills would go through. So it actually can be written in terms of an action of Lie algebra. So this minimally extended configuration space works. Now with the quantization, you can run essentially the same story. Epstein-Glaser renormalization works even for theories that are power counting non-renormalizable. So for each order in lambda in coupling constant and each order in h bar, you will get some finite counter terms that you add. Now, first thing you notice, if you do it for a bit, you realize that each time you get new counter terms. So for non-renormalizable theories, you add only finitely many counter terms at a given order in lambda, but they don't sum up to anything sort of finite, so your procedure doesn't terminate. But okay, you might not want to worry about it. You say, I have something which is an infinite series in lambda and h bar, and let's go ahead. Okay, so you can do that. So you can do the renormalization story. Then you ask yourself, is the quantum master equation satisfied? Actually, it is, because relativity, Einstein-Hilbert action satisfies these nice cohomological conditions. So that's great. All right, so I can define my BV operator. Great. So now you look at the space of gauge invariant observables. And this is when you see a problem, because you realize very quickly that there are no local gauge invariant observables. Okay, so then you have to bite the bullet and drop the locality condition, which is, I had to take that step in my life. I had to drop locality, although I like it very much. But if you want to talk about observables in quantum gravity, then that has to go, I'm afraid. But up to that point, things actually work out pretty nicely. So that's a very broad answer to a very broad question. Yeah, so there are various directions in quantum gravity. So there's one approach to quantum gravity called asymptotic safety, which posits that, we can actually use QFT methods in quantum gravity, but we have to, so I haven't talked about it, but from this renormalization group story, you can also derive flow equations. So in asymptotic safety, people say, well, maybe there is a fixed point, another non-Gaussian fixed point in our flow equations, and if we expand around that fixed point, then we have a theory which is renormalizable. That's what they say. They have some evidence in Euclidean that, they think this is going to work, so maybe that's going to work. And then, obviously, again, you can apply similar methods of quantum field theory, and everything is renormalizable. So that's one but that's the answer to one question. What to do with non-local observables? Well, there are some nice classes of observables, for example, relational observables, which are not local, but not far from local, so to say, because they describe relations between local fields. So this is what I've done in my paper with Brunetti and Frenhagen on perturbative randomization of gravity. So we looked at such observables. So this is doable. Obviously, these are only like little bits and pieces that we understand in the big picture, which we don't. But yeah.
And just the last one. So you specified when I asked the first question that for the Einstein-Hilbert action, what about an action expressed in the formalism of tetrals or something like that? Is it better or worse? Or?
Well, here, yeah, maybe I should refer you to papers of Schiavina, Alberto. So who else wrote about, do you have, yeah? Yeah, Giovanni Canepa, who was here but is not. Yeah, Giovanni Michele, yeah, I think, yeah. So they have done BV and even BFV for such actions. Thank you. And yeah, of course, you want to do everything with boundary now. But yeah, I have to go home. So. Yes.
So your theory is that whatever correction you need to make the quantum mass satisfied can be rephrased.
Yes. That's
even if there are potential obstructions.
No. If there are obstructions, then you're toast. Yeah.
The cohomology vanishes.
Yeah. So if the cohomology vanishes, then you can satisfy, right? But that amounts to redefinition of the time-ordered products. Yeah.
If the cohomology does not vanish, sometimes you might be able to satisfy.
Okay. So.
Does it always come from a randomization group?
Yeah, so if the cohomology doesn't vanish, you might be lucky because in that particular action, that particular coefficient vanishes. So then you have to sit down and calculate.
Yeah, but does it follow automatically that it can be?
Yes. If you can satisfy it in any way, yeah, then you're good. Yeah, sometimes you can be clever, sometimes you have to calculate. Yeah, thank you very much.